Alright, in this video I'm going to continue on with my discussion of solutions to the Schrodinger equation in an infinite rectangular potential well. And so we saw in the previous video that our k, which I then put a subscript n there to tell us that there are multiple k's here and that they can go up by an integer there, was equal to n pi over a, where remember a is the width of our potential well. So we have the potential well here, and where the potential is infinite on the sides and 0 in the middle, and it is a, the width of it. So it goes from x equals 0 to x equals a. And we saw in the previous video that we can then put this kn into our solution for the wave function, which, there are multiple wave functions depending on which k we use, which depends on what integer multiple of pi we use on here. And so I'll put n as a subscript on there, and then we had this a, which was our amplitude, and then we had that multiplied by e to the I knx, this is the kn from here, and minus e to the minus I knx, and that was all multiplied by a here. And then we saw that using that Euler identity, and we said that a prime was equal to 2ia, so we can just absorb that into the a prime. We said that this was equal to a prime sine of n pi x over lowercase a, which, as I said, is the width of our well here. But from here we want to normalize so that the probability equals just 1, so we don't get total probabilities above or below 1. And so we know that the probability from the Born rule, so if we took the probability of the entire wave function and we multiply it by its complex conjugate, you will often see it as squared, but remember, if there's complex numbers, that we have to actually multiply it by the complex conjugate. So it's the complex conjugate multiplied by of the wave function multiplied by the wave function here. And we want the total probability to equal 1. And so when we have one of these full, these total wave functions here, we can express that as, so if we have the wave function there, we can express that from 0 to a, the integral from 0 to a of all the different wave functions n, so for all the different k's here. And then we also want the dx there. And we can do the same thing for the complex conjugate. So that will be from 0 to a of the complex conjugate n here, dx. Okay, and so from this, since we know that we can express these two things like this, then we can express this as 1 equals the integral from 0 to a of n, and we'll do the complex conjugate there, and n dx, and then we just we substitute in this for these wave functions here. So we go from the integral from 0 to a of a prime sine of n pi x over a, and then we multiply that. So this one is the complex conjugate, then we multiply that by a prime sine of n pi x over lowercase a. So we end up with this, and this will be equal to, so that we multiply the a's by each other, and those can come outside the integral because it's just a constant. So we have a prime, the square of the magnitude of that, and then sine square of, oh yeah, the integral, control that better, the integral from 0 to a of sine squared, and that is n pi x over lowercase a dx. And so then we can take this, and so there is, I guess you could call it sort of an identity that I'm going to use here, which is that if we have the integral, some integral of sine squared of some constant, let's see, yeah, some constant, which is cx, that is equal to x over 2 minus sine of cx, or no, it should be, in fact, 2cx over 4c. And I'm not going to go through the whole integration. That's why I'm just using kind of this this identity here. And so we're going to do that. So we have our sine squared of some constant with x right here. And so I'm just going to kind of do this right here to this. And so what we end up getting for that is, so we get right here. So a prime, so squared. So we can kind of block this off and say this is just the identity I'm using while integrating this right here. And so what we have is we have this a prime squared multiplied by x over 2. So that is the same thing that we have here. And then that would be minus and sine of 2n pi x over lowercase a. All right, so that is kind of what we have here. So we just added that 2 onto it right here. And then down here is 4n pi over a, because this is our c right here. And so we just add that 4. And so this is what we get when we integrate this. But what we can see here is that, well, actually, this we have to evaluate this between 0 and a. But what we can see here to simplify this is that that sine 2n pi multiplied by 0 over a is just sine equals sine of 0, which is just 0. And if we have sine of 2n pi a over a, these a's cancel out, that's just 1, but we still have an integer multiple of pi, which is just 0. So sine of an integer multiple of pi is equal to 0. So this is 0 in all of these, and if x equals 0, then it's 0 again. So we just end up with a prime squared a over 2. And remember, that's still equal to 1. We have set this equal to 1. And so we end up with this. We can just multiply both sides by 2, divide both sides by lowercase a, and so we have a prime squared is equal to 2 over a. Then if we take the square root of that, we just have a prime equals the square root of 2 over a. And so this is our, remember this a is our amplitude. So going all the way back up to here, we absorb that 2i into it. But we, using this, we have said that a prime is equal to the square root of 2 over a. And if you're one of those mathematical people who are wondering also, because when you have a square root, you can say that the square root of 2 over a is actually equal to plus and minus a. This is just a matter of, so this should be a plus minus a. This is just a matter of the phase, which doesn't matter. So it doesn't matter that there's a negative here, but we're just going to use the positive a for this. And so we can now say, we can now show that our wave function here is, instead of putting that uppercase a, we now have 2 over lowercase a sine of n pi x over lowercase a. So this is now the wave function that we are using. And so we can actually use this wave function and plug it into the Schrodinger equation, which, if you remember, the time-independent Schrodinger equation is the minus h bar squared over 2m d psi over dx. Actually, this is the second derivative. Plus the potential equals the energy. But we said inside the well the potential is 0, so we can cross that off. And now if we plug this into here for psi, well, I'll take the first derivative first and then take the second derivative after that. So we have minus h bar squared over 2m. Then we have dx of this up here, which is 2 over a sine of n pi x over a. And so if we take the derivative of this, I mean, this could come out here. This is just a constant. But if we take the derivative of this sine here, so what we end up getting is we have negative h bar squared over 2m, 2 over a square root, and then the derivative would actually be, so you take the constant out, so that would be n pi over a, and then the sign changes to cosine, so it's cosine of n pi x over a. So that's the first derivative. Now we want to take the derivative of this, so I'll just say we're taking the dx of this, and then what we get from that is, once again, we pull out the constant here, and so I'll just write that down here. And so we still have the minus h bar squared over 2m. We still have the 2 over a here, but now we are pulling this out and multiplying again, so we have n squared pi squared over a squared, and this cosine, the derivative of that is minus sine, so I'll put that here, minus sine of n pi x over a. And we see here, we have this minus here, we have this minus here, so that becomes a positive. And so we can, I'll start over here, we have h bar squared 2m. We have our 2 over a here, square root, and then we have n squared pi squared over a squared, and then we have sine of n pi x over a. I probably should have written this different. So what I'll do is, to make it easier to read here, this I could have put sort of over here, and then it would be the 2 over a square root here. And so what we see here is, so we can just call this, once again, our psi, because that's just our psi. We already had that up here, but now we have this here, and if this should look familiar from the previous video, we said that En was equal to, well, I'll write it this way, the same way I had it in the previous video, n squared pi squared h bar squared over 2ma squared. And that is exactly what we have right here. And so when we say that, and so that tells us that that is a solution to the Schrodinger equation, because we wanted minus h bar squared over 2m d2 over dx squared. And like I said, we said that this was 0, because inside the well that's 0. And we said that that was equal to En. And we said En is equal to this, and when we took the second derivative of the wave function with respect to x, this is what we got from it. And so this is true. This is a solution to the Schrodinger equation. And this is, I mean, if you're not familiar with differential equations, that's what differential equations are, is you are given something. Maybe a quick simple example would be if you had something like dx. Well, actually, we want this to be the change in some function with respect to x, and so we would say that this is 2x. And then what you want to do in differential equations is actually look for a function. Instead of looking for what x equals, we actually want to find a function. And we know that the function that would fit this would be x squared, because the derivative of x squared is 2x. And so in differential equations, you are looking for functions that would satisfy this right here, and this function just happens to be the function that satisfies this. In the Schrodinger equation, we, like I said, we are given this right here, and we want to find the function that satisfies this, and that would be this function right here. So this is the wave function. It's the function that satisfies this equation right here, where we have E equal to this right here. And so that is, that's how you solve the Schrodinger equation. Is you're not looking for, you're not looking for x equals whatever like you do sort of in algebra. You're actually looking for a function. And so we're saying that there are multiple functions That's what this n here tells us. And the functions that satisfy this are ones that have any integer in for this n right here. So this a, as I said, is the width of our potential well. It's the width of that part of the well that has zero potential. And so there are multiple functions. So there's this where this equals 1. There's all this where this equals 2, 3, 4, so on and so forth. And so that's what I have here. This is actually pictures right out of the Student's Guide to the Schrodinger Equation book that I'm using for this by Daniel A. Fleisch. And so he put the waves for different n's in here. And if you've taken chemistry, you know that these n's are the principal quantum number, and so that's the energy levels of the electrons in an atom. But just sort of staying a little bit more general here, we're just saying that these are the energy levels of a particle in this infinite rectangular potential well. And so if n equals 1, then you would just have a 1 right there, and it's the pi squared h bar squared over 2 ma squared. And that gives us this right here. Then if you put a 2 in there, so it's n squared, so that makes it a 4, and that gives us this this sine wave right here. N equals 3, so 3 squared is 9. 4 squared is 16, going all the way up to 20, so 20 squared is 400. And we see that we're getting smaller and smaller wavelengths in here. So we know that that the k is inversely proportional to the wavelength. So as k goes up, which is what we have right here, that's what this n pi a. So the n pi a, which is what we have, n pi divided by a there. So as the k goes up, the wavelength reduces, and we get these smaller wavelengths here. And so this image right here is also from the Student's Guide to the Schrodinger Equation. And this is telling us about the parity of the wave function. So the parity. And so we see that that here it's even because it's the same on both sides of this center here. You see on this one they were still using x equals 0 to x equals a. This one, to make it a little bit clearer for the parity, they put x in the middle and put it from x equals minus a over 2 to x equals a over 2. But we see it's the same on both sides here, where this, it's opposite on both sides, so it's odd. So it goes even, odd, and it just goes back and forth that way. And so I actually liked the way that the quantum mechanics by the Griffiths book sort of summed this up. And so the first thing, it gives sort of 4 points about wave function. So wave function properties. And so the first one it said was talking about this. So so these are 4 wave function properties. The first one is alternate, odd, and even for the parity. The second one, and this is from, as I said, this is from Griffiths. So I'm kind of switching to a different book here. I mean, the Fleisch one, the Student's Guide one, does go through this, but I just like how the Griffiths one actually sort of enumerates this, and so that's why I'm kind of going from that one on this. And so the next thing it the Griffiths one says is that that each one up, so every time you go up one, you get plus 1 node. So a node is where it goes to 0 inside the well. So we see here this only goes to 0 on the edges of the well. So it has 0 nodes, whereas this one it goes to 0. So if we draw a line here, it goes to 0 right here. That's one node. Where this one, it now has 2 nodes. And then this one has 2, 3 nodes. So you get, every time you go up a level, you get one more node in it. And that was the number 2 in Griffiths. So 3 is that that each of these are mutually orthogonal. And what that means is that if we take the if we take this of this, well, that's m in complex conjugate multiplied by n dx. So if we take the integral of this, it equals 0 when m is not equal to n. And so that means if we take the integral of this one, for instance, multiplied by this one, it will be 0. If we take the integral of this one multiplied by itself, then we get the probability. That would just be the Born rule. But if we do it this way, then when m does not equal n, rather. And so in Griffiths, and this wasn't a very good picture, but he actually goes through this proof of it here. So you can, I guess, pause or look this up or buy the Griffiths book or whatever if you want to look at that. I wanted to do a little bit more of an intuitive approach to it. And so if we take the n equals 1 and the n equals 2 wave functions here and multiply them, what we get is this. And so we're essentially kind of scaling these up by an amount that depends on this. And so right here we are sort of adding this, if we split that in half, adding this onto this, and then adding this onto this downward, so that we end up with this larger amplitude here. But now if we take the integral, which is just a sum, it's a continuous summation. We are taking the sum of all this, which is some positive number, and then adding that to the sum of all this, which is the same magnitude but now negative, and so that would be equal to 0. And so that's how, that's sort of intuitively, I guess graphically, how you can see that if you take the integral of any of these multiplied by each other, then you will get 0. And that tells you that they are orthogonal. And because we normalized it, which I spent a bit of time on earlier in the video, where we ended up getting that, that 2 over a thing, we can actually say that because this is orthogonal and we normalized it, that it is orthonormal. And so we can actually sort of simplify this, and we can actually say that if we take the integral, complex conjugate m multiplied by n dx, that this is equal to the Kronecker delta. The Kronecker delta being defined so that it's 0 if m does not equal n, and 1 if m equals n. And so the fourth thing that the Griffiths book points out as a property of wave functions is that it is complete. And what that means is that that for any wave function, any sort of generic wave function here, you can get this as a linear combination of other wave functions. So we can say that that is equal to a linear combination from n equals 1 to infinity um, of, so Cn, which is some constant, with Cn will be less than 1. I guess it could be less than or equal to 1. And so it'll be have that Cn and then our wave function n here. And so that that we can say will be the a, or 2 over a rather, 2 over a multiplied by the summation from n equals 1 to infinity of Cn sine of n pi x over a. And so this, well, if you know your like Fourier analysis, you know that this is the Fourier, yeah, Fourier, Fourier series, and that this is actually what's called Dirichlet's, Dirichlet's theorem. So that's what this is. This idea that that we can get this wave function here as a linear combination of these wave functions here. And so what we can say then is that that if we take the integral of this wave function, which we can say is a wave function that satisfies the Schrodinger equation, and then this one, which is a linear combination of other wave functions, then we can say that this is equal to the summation from n equals 1 to infinity of Cn, and then the multiplied by the integral of the complex conjugate here, yeah, that's m, and then this one here, because we said that this is equal to this summation of Cn times this. So we have the Cn and that there, so that's all still there. That's what the f of x here is equal to. And then from this, and that should have a dx there, so dx. And from here, we can say then that this is the summation from n equals 1 to infinity of Cn, and then the Kronecker delta mn, and that this is equal to Cm. And so this is the way that we can actually find out what these Cm or Cn are. So when we want, I guess I should point out what these constants are, and they are, well, they're the probability. Well, if you square it, it's the probability. So C equals the probability. If it's just without squaring it, then it's the prob amplitude. And so, yeah, they essentially just tell you how much of a particular wave function is a part of it. So if we want to make it a little bit clearer up here, it was getting a little bit crowded down there, we can say that we have our wave function here, and it is a combination of other wave functions here. So we have the Cn and then psi n. And this is just C1 psi 1 plus C2 psi 2 plus C3 psi 3, so on and so forth. Uh, and so each of these is just sort of a weight, a a weight. So if you've ever taken like a weighted average or something, it's the weight. It's how much of this wave function here is a part of this sort of, I guess, total wave function. And then how much of this tells us how much of psi 2 is this. And we know that if we have Cn squared, so going from n equals 1 to, I guess we don't doesn't need to be infinity, that this has to equal 1, because this is the probability, and probabilities have to always add up to 1. And so the square of this, as I said, is the probability. Without the squaring, it's the probability amplitude, which is that sort of weird thing that doesn't have much of a physical interpretation, as far as I can tell, than using the Born rule. We know that squaring it gives us the probability. And so if we take the square of it and add up all the squares of them, it should come to 1. But this fourth point here, as I said, is the completeness, where we can get wave functions that are linear combinations of any other wave functions. So I don't know if you know anything about like group theory, where group theory tells us that if we have two members of a group A and B, and we perform some operation on them, we get C. That C also has to be a member of that group. And that is the completeness of the group. Uh, I'll I'll probably make some videos about group theory, maybe somewhere further into the future, after we get through everything about the Schrodinger equation and stuff, because this is what is you need this to really get even further into quantum mechanics and into quantum field theory and things like that. This uh, group theory. But anyway, that's it's the completeness idea here is what we are interested in, and that's essentially saying that any wave function here uh, is part of the group of wave functions, and it can be made from a linear combination of any other group of or any other or, yeah, a linear combination of other wave functions. So yeah, that is everything I wanted to talk about in this video. So just to sort of review here, we normalized this the wave function here so that we could use it as a probability. Um, and after that, I showed how if we plug this into the Schrodinger equation and we assumed that V was equal to 0, that the potential is 0 inside the well. So we plugged it into the Schrodinger equation for this psi here, and we saw that we ended up getting exactly what we needed, or it showed that that this here is a solution to the Schrodinger equation, and it tells us the energy here. And in the next video, I'm going to get into some other operators, in particular the the momentum operator for the Schrodinger equation. And then we saw that we can have these multiple solutions here. Um, so I was just talking about this linear combination here. I guess I should sort of maybe give a little bit more of a physical interpretation of that, if that's not going too far. So we said that it's a linear combination uh, from n equals 1 to n, large n there, of Cn psi n. And so this psi n here can be the various solutions that we have here, where we can have 1 or 2 or 3 for the n there, going all the way up there. Uh, and so when we say that we have a linear combination, uh, that is also the the same thing as saying that we have a superposition. And of course, this is not superposition uh, just in terms of position. It's a superposition of energy in, I guess, what you would call energy space. So that's saying if we have a particle and it's in this state, when we measure it, it will collapse into maybe psi 1 or psi 2 or psi 3. And the probability of it collapsing into psi 1 is C1 squared. The probability of it collapsing into psi 2 is C2 squared, and so on for C3 squared, and on until, I guess, infinity, really. Uh, in an infinite potential well, then n goes to infinity. We'll see, as I said in later videos, that if we have a finite potential well, then it does not go to infinity. Because if you get enough energy, then so if you have a well like this, where these are not infinite, if you get enough energy, your particle is going to escape it and no longer be in the well. But anyway, so when you hear people talk about the superposition of the particle or the collapse of the wave function, that's what this is. But anyway, um, uh, yeah, just to reiterate the four wave function properties from Griffiths. We have this alternating odd and even parity, which I showed right here. This picture is from the Student's Guide to the Schrodinger Equation. Uh, each of them has another node. Every time we go up in energy level, we add another node onto it. They are mutually orthogonal. So if you take, if you add up all of these, if m does not equal n, then the integral will equal 0. The integral just being a continuous sum, and they are complete. So alternating, each plus one node, mutually orthogonal, and complete. But anyway, I hope you found this video helpful, and I hope that the Schrodinger equation is starting to make more and more sense with each of these videos. I think there is one more video I will be making about the infinite potential well before I get to the finite rectangular potential well and then the harmonic oscillator and so forth. So I will see you in the next video.